This is Introductory Nuclear Physics that today we are going to talk, and it is lecture number 2, the Bohr's Atomic Model. I am Dr. Nasir M Mirza, and today I am talking about the Bohr's Atomic Model. I come from Pakistan Institute of Engineering and Applied Sciences. In abbreviation, it is PIAS. Let us recap the Rutherford's ideas on atomic model. Rutherford and Geiger and Marsden tested pudding model by bombarding gold foils with alpha particles. And then they disapproved the J.J. Thomson's model. They showed that the alpha particles were not deflected at all, while some of the particles were deflected significantly. So the question was why these deflected particles are coming. And the solar system model was suggested, and it was proposed that the nucleus is very small, and perhaps it is as small as 10 to the power 4 times smaller as compared to the atomic diameter. If the model of the atom is correct, proposed by Rutherford, then accelerating electrons will have to radiate energy and will collapse into the nucleus. The continuous range of radiation frequency should have a continuous spectrum. On contrary, all atoms have shown a discrete line spectrum. There were serious problems with the Rutherford model, and it did not explain atoms' negatively charged electrons' location in the space surrounding the positively charged nucleus. It did not explain why electrons do not fall into the center. As we know, oppositely charged particles attract each other. Then electrons should collapse into atoms' center, yet atoms are billions of years old. They are stable. At least the majority of them are very stable. So what prevents negative electrons from being drawn into positive nucleus? It also never explained the spectrum of atom. Electromagnetic theory says that electrons are moving around a center in a circle, so they must give off energy in continuous fashion. However, atoms have discrete spectrum. Whenever you measure spectrum, you get discrete lines. These problems in Rutherford model were due to the fact that classical physics was used to interpret and develop Rutherford's model. And classical physics fails to provide a meaningful analysis of atomic structures because of its pure particle or a pure wave approach. Rutherford model, as we have seen, had problems. Bohr atomic model combined both classical and modern notion, the modern notion of wave-particle duality, and provided a very good atomic model. The new model was needed, and the reasons behind the new model for atom were that we knew so far small dense center with a positively charged nucleus, small light, very small mass, negatively charged subcomponents that are circling around the nucleus, electrons. Later addition of neutrons inside the nucleus after 1932. It should explain why and where the electrons are located. It should also explain the stability of atoms. It should talk about the energy emitted and energy absorbed into the atom. So Bohr's atomic model was proposed, and it was based on various observations. And let us first talk about these observations. When we heat hydrogen gas, bright visible light is emitted at discrete wavelengths, and it is not a continuous spectrum. Other gases also behave in the same way. They produce discrete wavelengths, but each gas has a unique wavelength, and that's how the elements are identified. Before we talk further about the Bohr's model, let us first discuss electromagnetic waves and the spectrum. The electromagnetic waves, basically, if you look at the radio sounding, or you watch television, or you cook dinner in a microwave oven, then you are basically using electromagnetic waves. Radio waves, television waves, microwaves, all are the type of electromagnetic waves. When there is fire, you see visible light. Fire emits visible light. It is a form of electromagnetic waves. When you see vegetables, it is due to the reflection that is the absorption and then emission from the vegetables, the visible spectrum of light, and all are electromagnetic waves. They only differ from each other in wavelength or frequency. If we want to look at the electromagnetic waves and its spectrum, let us first concentrate on wavelengths. Wavelengths are measured in meters, and they vary from 10 to the power 3, called longer wavelengths, to 10 to the power minus 12, the shorter one, in meters. So very short wavelengths and very long wavelengths. And in between, you see 10 to the power 2, 10 to the power 1 and 1 and 10.1, and 10 to the power minus 4, 10 to the power minus 6. And if I compare things, then 10 to the power minus 3 meters, about a dot or a period, and the dimensions of the cell are of the order of 10 to the power minus 4 to 10 to the power minus 5, and bacteria is as small as the micrometers, and then we have viruses, and then proteins are of the order of 10 to the power minus 8 meters, and then the water molecules are of the order of 10 to the power minus 10 meters, and even shorter distances are with the nucleus radius. The wavelengths. The common names for the wavelengths of electromagnetic radiations, the spectrum from 10 to the power 3 to 10 to the power minus 1 is roughly termed as radio waves. And then comes the microwave region, which is 0.1 to 10 to the power minus 3 to 10 to the power minus 4. And then comes the infrared region. Infrared region is from 10 to the power minus 4 to 10 to the power minus 6. And then there is very, very short, small region in between the 10 to the power minus 6 and 10 to the power minus 7. This region is a visible light region. And then comes the ultraviolet region, which is spread over 10 to the power minus 7 to 10 to the power minus 8. And from 10 to the power minus 8 to 10 to the power minus 10 is the soft X-rays region. And then comes the hard X-rays and gamma rays region, which varies from 10 to the power minus 10 to 10 to the power minus 12 meters. The gamma rays have this much wavelength, very short wavelengths, and very long wavelengths are associated with the radio waves. The sources for these radiations you can see are the AM radio, the RF cavity, the radio frequency transmission services, the microwave ovens, and then microwaves and the radars. They operate in microwave region, and then people emit the thermal radiations in infrared region. The light bulb is in the visible light region, and then comes the soft X-rays used for the medical purposes, the X-rays machines, and then we have radioactive sources are hard X-rays or the gamma rays. They have the special purposes for nuclear medicine. The frequency, as opposed to the wavelength, is a lower frequency region. When we talk about the radio waves, it is 10 to the power 6 to 10 to the power 9 region. And then microwave region, 10 to the power 9 to 10 to the power 10. And then it is separated up till 10 to the power 11. From 10 to the power 12 to 10 to the power 14 is infrared. And 10 to the power 14 to 10 to the power 16 ultraviolet, in between visible region. And then we have the frequencies of for soft X-rays and hard X-rays going up till 10 to the power 20 cycles per second. The energy measurements are done generally in electron volts, and the energies for these electromagnetic waves are measured in EV, varying from 10 to the power minus 9 electron volt to 10 to the power 6 electron volt, which is mega electron volt. So gamma rays have the mega electron volt energies, and the X-rays have the kilo electron volt energies, and the light bulb has of the order of 1 to 10 electron volt energies, and the radio frequencies are having energies as low as 10 to the power minus 9 to 10 to the power minus 6. And the microwave region is from 10 to the power minus 5 to 10 to the power minus 3. Infrared region is from 10 to the power minus 2 to 1 electron volt. So electromagnetic waves are represented either in wavelengths, or by their sources, or by the frequencies measured in waves per second, or by their energies in electron volts. You can see here the gamma rays have very short wavelengths, and the radio waves are of very large wavelengths. The visible light is hidden somewhere in a middle. If you want to measure the properties of such waves, then they have the positive amplitudes and the negative amplitudes. They are measured with the help of the wavelengths. The wavelengths are the distances between one crust to another crust, or one position to another same duplicated position in the cycle. So wavelengths are representative of the cycle, and the number of cycles that pass through one position in 1 second are the frequencies. And if you want to look at the visible light spectrum, it varies from the red region to the violet region, and it has the red and the orange and the yellow and the green and the blue and the violet color, the color of the rainbow. You can see here the violet color, the blue, and going to the red, and then infrared regions. The northern lights are famous for their spectacular displays, and these are also called Aurora belt, Borealis belts, and they are really visible near the North Pole. It is due to the charged particles that are trapped in the Earth's magnetic field, and they keep on falling towards the North Pole, and when they fall in the showers, and then they start emitting continuous radiations in the form of electromagnetic rays. And the northern lights are formed and people go and watch them. Now we come back to the atomic model again after this brief discussion and introduction to electromagnetic radiations. The quantum concepts are very clear when we look at the energy levels and the spectrum. Various colors of the rainbow have different values of energies associated with them, and there are the forms of light that are not really visible to human eyes, but human can see only a small portion of the visible spectrum. The infrared and ultraviolets are not really that much visible to us. However, insects and other animals probably have the detectors detecting eyes to look that part of the spectrum as well. Max Planck, who is responsible for telling us about the black body radiations, and the Einstein in his photoelectric effect, figured out that the energy comes in little chunks or the quanta, and in this way the light behaves like particles. The light particles were called photons. So it was a quantum concept. They predicted that these light waves are behaving like light particles. Max Planck also proposed that the energy radiation occurs in discrete units, and he referred it to the quantum concept. That is, the exchange of energy takes place in a discrete form. It is not the continuous variation of energy that takes place when energy is transferred from the electromagnetic waves. So one part of the Bohr model was based on this, that the electrons orbit around the nucleus of atom at a fixed distance from the nucleus and have definite energies, and they keep the distance fixed. And they do not radiate any energy when they are orbiting around in a fixed orbit. Their energy levels remain fixed. Let us briefly discuss the atomic spectra. And this is the idealized laboratory arrangement for observation of such atomic spectra. Here we have a gas tube, and it is heated with the help of electric current. And in this vacuum tube, the radiations are emitted, and they are emitted everywhere. And there is a board, and there is a slit available through which the light passes. And it hits the prism, and it is diffracted from the prism, and then it splits according to the wavelength of the light, and the different parts of the light go to different wavelengths, and therefore they are split. So the spectrum is a graph in which there is, on y-axis there is intensity, and on x-axis there is wavelength, and we have the very bright and very dim light line, and that is indicator of the intensity, and the line itself is telling us about the wavelength. So this experimental setup was used to find out the spectrum for various gases. The gases were changed, and elements were changed, the molecules were changed, and all contained discrete wavelengths. Let us first look at the hydrogen line spectrum. And you can see a very fine bluish line, and a very dim violet line. And then there is a line in the red region. We have in the background the whole rainbow spectrum, and this is a standard hydrogen line spectrum. One line occurring in the red region, another line occurring in the blue, and another line in the violet, and all have different wavelengths. So in between there are no lines. So this is the discreteness. The intensity, how bright it is on the scale. So the spectrum is basically the wavelength versus the intensity. Helium spectrum, if you look, you see a very shining yellow. Yellow is always very popular with our eyes. Our eyes immediately detect yellow. And there is a reddish tinged line, which is at a different position as compared to the hydrogen. And there are lines in the green part and in the bluish region, and then the violet regions. These are all helium lines. Then there are the lithium line spectrum, and you can see it's not exactly yellow, it is going towards the orange, orangish yellow, and this is red, and this is green, and this is towards the blue and absolutely violet and ultra region. So lithium lines, you can see that each individual line spectrum indicates the element, and for each element this is a signature. It is different for each element. These experimental line spectra for various elements were measured, and then they were the graphs were made available with the help of a black body radiation, which had a continuous all types of wavelengths available. These were really the signatures and the dictionary-like situation in which element was really identifiable with the help of the line spectrum. It was an emission line spectrum because the particular element was heated and the light was emitted. So we have the idea with the help of these two gentlemen, Rutherford and J.J. Thomson. They are discussing things. Let us recap this, that most of the atom is empty. According to them, almost all mass of the atom is at the center of the atom, and it is the nucleus. The electrons are part of the atom. Electrons are circling around. Electrons are negatively charged ones. The nucleus is positively charged thing, and it is a hard mass. It is containing almost all mass. So these were the ideas at that time when Rutherford and J.J. Thomson had a notion about the atom. And we had the emission line spectrum. These figures were showing the emission line spectrum, and it was a spectra which is basically due to the emission of light in a visible region. And every element was displaying a unique spectrum, and this vapor phase excitement was giving rise to these. So each individual element was identifiable with the help of a particular spectrum. Atomic spectroscopy became a very useful tool to analyze the composition of unknown substances, even the substances that were at very large distances from Earth. When you see their emission line spectrum, you can tell which one is where and how much. Then people went on figuring out the empirical formulas for line spectrum, and the spectral lines originating from the emission spectra were obeying certain transitions and series. And they were termed in 19th century as empirical relations. They were based on fitting curve, and the one such series is the Lyman series. The Lyman series contains the wavelength of a specific type in which 1/λ is occurring here, and 1/λ is equal to r times 1/2 square minus 1/n square, and n is basically changing from 2, 3, 4, 5, and as you can see here in the Lyman series, it is for 2, 3, 4, 5, 6, and so on. We will come soon to know that these were really very important numbers. Similarly, Bohr series, here the 3 is as a correction. The Bohr series starts from 3. and the R, which was a quantity measured, and it was the same for every formula. It was termed as a Rydberg's number, and its value was 1.099 into 10 to the power 7 meter inverse. There were other spectral series in the infrared region that were seen to obey the empirical relations, and for example, Paston series, the Beckett series, the Fund series, and remarks are that the R value remains same in all series, and the formula had a remarkable similarity, and the spectral lines were also shown to have limit when n goes to infinity. They have the limiting values 1 over lambda. The lambda is the wavelength measured in the units of length, the meters or micrometers. So we come back to the Bohr's model and the ideas behind the Bohr's model. The electrons can circle in a nucleus only in the allowed state. When an electron is in one of these orbits, the atoms are having a fixed definite energy. The electrons in hydrogen atom are at its lowest energy level when it is in the orbit which is closest to the nucleus. Orbits that are separated by the empty space, in those places, electrons will not exist, will not stay. While in orbit, electrons can neither gain energy nor lose energy, so this was fixed. So the stability. But the electron can gain energy equal to the difference between the higher and the lower orbits, and therefore they can move to the higher orbits. And this was termed as absorption. Similarly, when an electron falls from the high state to the low state, the energy is emitted, and this was termed as emission. So Bohr's atomic model considered a simple hydrogen atom with a single electron which was circulating about the nucleus, having positive charge. The radius of the circle is r, and the speed is v along the tangent to the circle, and the attractive Coulomb force is providing the centripetal force, and it is this kind of arrangement. The force is due to the Coulomb force. It is between two charges, Q1, Q2 divided by R square, and 1 over 4 pi epsilon naught is this relationship for the Coulomb force. And the force due to the centripetal acceleration is balanced. This is mv square over r, where v is the velocity, r is the radius. So if we equate these two, we get the kinetic energy, which is mv square by 2, equal to e square divided by 8 pi epsilon naught times r. The potential energy for such a system in which there is a Coulomb force is given by minus e square divided by 4 pi epsilon naught times r. It is 1 over r with a minus sign. The force is a Coulombic force, then the potential energy is behaving like 1 over r. So the total energy is the sum of these two energies, and if we write down both of them and add them, we get this 1 over 8 pi epsilon naught with minus sign and e square divided by r. This is the total energy. The first postulate is that electrons will circle a nucleus without radiating energy, provided that its orbit contains an integral number of de Broglie wavelengths. What is de Broglie wavelength? According to de Broglie, every particle has associated wave, and the wave has a wavelength. So that idea was used. The particle and the wave duality was used. Or we can say that the angular momentum of the electron is quantized. This was later postulated. But the first idea was this: let us choose integral number of de Broglie waves to fit an orbit. The circumference must be such that it must be equal to the de Broglie 1, de Broglie 2, de Broglie 3 wavelengths, 1, 2, 3, 4, not half, not 3 by 2. It must be integral number of de Broglie wavelengths. So n times lambda, the number of de Broglie wavelengths, must be equal to 2 pi r, which is the circumference of the circle, where r is a particular r, r sub n, and n is for the first orbit, the second orbit, or third orbit. It will change if n is changed. And this postulate is a very strong indicator that we are now incorporating the particle and wave duality in one picture. R is the radius of the orbit, and it contains n wavelengths. Therefore, lambda is equal to h divided by m into v. According to de Broglie, the momentum is m into v, and h is the Planck's constant. Therefore, velocity was estimated through this relation, using both of them, and we find that the n, the radius r can be estimated through this velocity equation and also the above balance equation with the help of the wavelength, and it's a relationship with the m into v and the total energy. Then we come to know that Rn is basically proportional to n squared. And the other constants are h square epsilon naught divided by pi, the mass of the electron, and E, the charge of the electron squared, where n can be 1, 2, 3, 4. So it is proportional to n squared. This n was called the quantum number for the orbit, or orbital quantum number, or principal quantum number. This n is an integer, and it puts wavelengths fixed. So the radius of the innermost orbit is this, where n is equal to 1. So the rest of the radii are given in terms of the Bohr radius. This is the innermost radius, which is n is equal to 1 value, and the rest of the values can be estimated through a n square formula, and we can see that the innermost radius has a certain value, and you can calculate with the help of h square epsilon naught divided by pi m into e square, and it is roughly 5.3 into 10 to the power minus 11 meters. Which is roughly 0.5 into 10 to the power minus 10 meters, minus 10 to the power minus 10 meters, angstrom. Now let's talk about the energy levels. The total energy is the kinetic energy and the potential energy, and the total energy is given by the sum of these two energies, and we have this value as minus e square divided by minus e square divided by 8 pi epsilon naught times r. And the total energy of the atomic electron is negative, which means that it is not a free electron, it is a bound electron. Whenever we find a minus sign, it shows the attractive potentials work on it, and it is not allowing to be released. You have to give this much energy to get it released. So it was a negative, and it is necessary for the bounded electrons to the nucleus when they are orbiting with a given radius as Rn, then the energy is given through this. And so here R is converted into Rn, and its value in terms of R A0 and N square is written. So we get a formula which says that the energy of the moving electron in a particular orbit is proportional to 1 over n square. And the smallest value of n is 1, and therefore that is the energy of the lowest orbit, or the closest orbit to the nucleus. So these energies were called the energy levels for the hydrogen atom, and energy levels were measured in terms of the N, which is a quantization, the principal quantization for the states. The electrons can have states. So Bohr's model, second postulate, was followed. Electrons in hydrogen can exist only in certain specific energy states without radiating any energy at all. When they undergo a transition from high energy level to low energy level, they are going to emit electromagnetic radiation with the energy h nu with the frequency nu. They will absorb the energy if they are going from lower energy level to higher energy level. So initial energy minus the final energy will be the photon energy, either absorbed or emitted. And it will have h into nu value. The nu is the frequency, h is the Planck's constant. So each energy emission or absorption will take place in form of a quanta. And the quanta will be based on the small value of h. So we get a picture. The picture is this. The ground state is n is equal to 1. The excited states is n is equal to 2, n is equal to 3, n is equal to 4, and so on up till n is equal to infinity. Once n is equal to infinity, the electron becomes free enough to move away from the nucleus. The lowest, the ground state energy in terms of the joules is given here, but nobody is using joules anymore. They convert this energy into electron volts. And 1 electron volt is equal to 1.602 into 10 to the power minus 19 joules in energy, in the energy levels, and we can convert the energy into electron volts. The conversion factor is 1.6 into 10 to the power minus 19. And we can see that when electron falls from initial energy to final energy, then it emits the energy in the form of photon, and it is h nu. The nu is the frequency. That was the second postulate of Bohr's atom. We move further in this, that when we substitute the energies, we get the initial and final state of the hydrogen atom and corresponding the new quantum numbers Ni, the N initial and N final, and the energies are given in the form of energy difference. And in terms of the photon wavelength, this is given by the relationship which has this factor 1 divided by N final square minus 1 divided by N initial square, and this is looking like the formulas that were really empirical spectral series formula. We can choose N final and then find out the similar relationships that were really given originally by the empirical relationships. And we see the great similarity, not only similarity, but we find that Rydberg's constant is exactly the same. And therefore, the Bohr's atomic model is reproducing the experimental results, and it is identical in the form with the spectral lines. And therefore, the steps that were taken to interpret the atom that were correct. So when electron falls from high energy level to low energy level, it starts emitting photons, and the wavelength of the photon can be computed using this relationship, and the quantum numbers are really responsible. So the quantized energy levels in the hydrogen atom are like this, that the ground state has minus 13.6 electron volt, and the first excited state has the energy level of minus 3.4 electron volts, and the next higher is that. And we can see that if the electron falls to the ground state from any of the energy level, then it is going to produce the Lyman series. And if it is going to fall to the first excited state, which is for n is equal to 2, then it is going to produce the Balmer series. All the electrons that are going to fall to this level from any state are going to produce Balmer series. Similarly, the Paschen series, any electron which falls from higher energy level to this n is equal to 3 state, or the second excited state, will produce the Paschen series. And that's how the quantized energy levels are behaving. We see that the difference between the ground state and the first excited state is the gap is large, and the gap starts decreasing as we move up. And for n is equal to infinity, the ground state, the free state is for the 0 electron volt, and all these are the bound states, and therefore they are shown with the negative sign. So Bohr's atomic model had a similarity of solar system. It had a similarity of central nucleus, and the electrons revolving around the nucleus, and the first state, excited state, the second excited state, the ground state, and the first excited state, and the second excited state, n is equal to 1, n is equal to 2, and so on, are given. And the series, the Lyman series, the Balmer series, the Paschen series, and the bracket series, and the front series are really visible, and Bohr's model works very well, and it is very similar to the solar system. So the atom has excitations and de-excitations. If some energy is given to the electron, in this, if the exact amount of energy is given, it will move from the innermost state to the first excited state, and this will be the atomic excitation. And if the electron moves from the high energy state to the low energy state, it will emit the energy Hc divided by lambda, or h nu. Then it will de-excite, and the de-excited electron will fall to the ground state, and it is shown like this. These were the diagrams that were used and shown to depict that the wavelengths absorbed and wavelengths emitted can be exactly determined with the help of Bohr's atomic model, and the formulas can be used, and we can exactly measure them, the absorption spectrum and the emitted emission spectrum can be explained. Very briefly about the Bohr, he was educated in Denmark. He lived and worked and died there, and he had a remarkable impact on science and the history. At the University of Copenhagen, he studied physics, and he received his doctorate in England and was granted study work under J.J. Thomson. He won Nobel Prize for his atomic model. And this is a picture where he's standing with the Max Planck. And in the background, we see the equations, the Maxwell's equations, and the effects that were depicted by the Bohr's idea that the energy levels and the excited and de-excited states also emit the photons. So electromagnetic theory had these both combinations. This is a picture which is showing the Bohr's interaction with Heisenberg. Heisenberg is very popular for his uncertainty principle, and both of them are responsible for telling us about the stationary waves that are the electrons within the atom. So Niels Bohr's model for atoms suggests discrete energy levels, and the wave-particle duality-based explanation for a hydrogen atom. And soon the quantum mechanics was created at a microscopic level, and Pauli suggested that many electron atoms should obey the Pauli exclusion principles for filling up the various energy levels, and that's how the energies and the shells were filled. Also the neutron was discovered by James Chadwick, and its properties were determined, and it was part of the nucleus for heavy atoms, and that's how the atom's picture was complete. In our next lecture, we will talk more about the quantum part of the atom, and we will explain further how the quantum mechanics was influencing the atomic and nuclear model. So wait for the next lecture. We stop here, and thank you so much.